Good day, everyone. My name is Charles, and I'm from DC Pet 31. Today, I'll be reflecting on the 5 videos about chip manufacturing. When I first watched the video Chip Manufacturing, I was honestly amazed by how much precision and complexity goes into making the chips that we use every single day. What seemed like a simple component inside a phone or laptop turned out to be one of the most complicated things that humans have ever engineered. This video explained how chips start from something as common as sand, which is processed into pure silicon. This silicon becomes the foundation of semiconductors that power almost all modern devices. I learned that these silicon wafers are created by melting purified silicon and forming it into a perfect crystal structure called a monocrystal. This crystal is then sliced into thin circular wafers, which serve as the base for all microscopic components that will be built on top. From there, the wafers go through numerous manufacturing stages inside ultra-cleaning environments called clean rooms. The video also mentioned that these rooms are over 100,000 times cleaner than hospital operating rooms. That level of cleanliness is necessary because even a single particle of dust can destroy a chip worth thousands of dollars. It made me realize how much discipline, precision, and technology is required to make something that most of us take for granted. As the video went deeper into the manufacturing process, it introduced several technical steps. One of them was oxidation, where the wafer surface is exposed to oxygen to form a thin layer of silicon dioxide. This layer acts as an insulator and a protective barrier. Then comes photolithography, one of the most critical steps in chip making. It's where ultraviolet light is used to transfer circuit patterns onto the wafer, similar to how a projector transfers an image onto a screen. A photosensitive material called a photoresist is applied, exposed to UV light through a patterned mask, and then developed to reveal precise areas where the material will be removed or added. Another step is etching, which removes unprotected areas of the wafer surface to carve out circuit paths. The precision here is unbelievable. We're talking about etching lines smaller than the wavelength of light. After that, there's doping and ion implantation, which modify the wafer's electrical properties. This is done by bombarding the silicon with dopant atoms like boron or phosphorus, allowing engineers to control how electricity flows through different regions of the transistor. Learning about these steps helped me understand how transistors, the building blocks of CPUs, are formed and tuned for performance. The second video, Why Chip Making is So Hard, gave me a whole new appreciation for how challenging and expensive this industry really is. It explained that a single semiconductor fabrication plant, or fab for short, can cost over $10 billion to build. That's because the machines needed for photolithography, ion implantation, and wafer processing are extremely advanced and expensive. One example mentioned was the EUV, or extreme ultraviolet lithography machine made by ASML, which costs more than $150 million each. The video also highlighted how chip making isn't just a technical issue, it's a global and geopolitical. Chips power everything from smartphones and AI servers to cars and defense systems, so whoever leads the semiconductor manufacturing holds enormous economic and strategic power. The complexity of the supply chain, with materials sourced from one country equipment to another and assembly in a third, makes it even harder to manage. Watching that made me realize that computer engineering isn't just about design or coding anymore. It's a part of a massive ecosystem that will influence the world and continue to influence the world. Then came the third video, which is photolithography, which went deep into that critical process I mentioned earlier. It was fascinating to see how engineers use light to print nanoscale patterns onto wafers. The video showed how ultraviolet light passes through masks containing intricate circuit print layouts, projecting them onto the photoresist-coated wafer. The exposed areas become soluble and are washed away, leaving behind tiny features that define transistor gates and interconnects. What impressed me the most was the precision required. We're talking about features measured in nanometers, smaller than a single virus. The alignment between each layer has to be perfect because the chips are built up in dozens of layers stacked on top of each other. Even a misalignment of a few nanometers could render the entire wafer useless. I also learned that modern photolithography uses deep ultraviolet or extreme ultraviolet light, which allows for even smaller patterns and higher transistor density. This process truly represents the intersection of physics, chemistry, and engineering, where light is used to sculpt matter on an atomic scale. The fourth video, how a CPU is made, tied everything together perfectly. It showed the entire journey from raw silicon to a finished central processing unit. All the photolithography, doping, and etching process are complete. The wafer contains billions of transistors interconnected by the microscopic copper wires. These interconnects are made by filling etched trenches with copper, then polishing the surface until it's perfectly flat. Copper replaced aluminum because it has lower electrical resistance, allowing faster and more efficient signal transmission. Once the wafer is complete, it undergoes testing to ensure that every chip functions correctly. Then it's cut into individual dies using fine saw blades. Each die is then packaged, which means connecting it to external pins and encasing it in a protective shell so it can be safely installed onto a computer motherboard. The video also explained how different methods, such as flip chip bonding, are used to attach the chip to the substrate. This process makes sure that the signals can travel quickly and reliably between the chip and the rest of the system. Seeing how much effort goes into producing something smaller than a fingernail gave me a new level of respect for the people behind these technologies. Finally, the fifth video, Future Trends of the Computer Engineering Profession, looked forward to what's next in our field. It discussed how computing is entering a new era driven by artificial intelligence, quantum computing, 5G networks, robotics, and IoT. These technologies are demanding and more powerful, efficient, and specialized chips than ever before. For example, AI accelerators like GPUs and TPUs are designed specifically to handle complex machine learning tasks, while quantum processors use qubits to perform calculations far beyond the reach of classical computers. The video also emphasized how future computer engineers will need to master both hardware and software, since innovation now happens at the intersection of two. It's not enough to just design faster processors. We also need to think about energy efficiency, scalability, and reliability, as well as sustainability. One important topic mentioned was green computing, which focuses on designing chips and systems that reduce power consumption and minimize environmental impact. I think that's something our generation of engineers must take seriously, especially given how resource-intensive semiconductor manufacturing is. After watching all these videos, I realized that chip making represents the peak of human innovation. It's the perfect example of how physics, chemistry, material science, and computer engineering all come together to achieve something extraordinary. Each video built on the last, from understanding the raw process of making chips to recognizing why it's so difficult, to seeing the detailed mechanisms like photolithography and ion implantation, and finally to imagining the future that we're heading toward. For me, the biggest takeaway is that computer engineering is not just about circuits or programming. It's about pushing the limits of what's possible, solving problems that seem impossible, and continuously learning as the technology evolves. These videos remind me that something even invisible to the eye, like a single transistor, can contain the power to change the world. As a computer engineering student specializing in networking, this series made me realize how interconnected everything is. From the chips that process data to the networks that transmit it. Whether I end up working in network systems, embedded software, or semiconductor design, the principles behind chip manufacturing, precision, patience, and innovation will always apply. In the end, these videos didn't just teach me about chip making, they showed me the dedication, collaboration, and brilliance behind every piece of technology that we use. And more importantly, they reminded me that our future, the future of our profession, isn't just about keeping up with change, it's about leading it. That's all from me. Thank you.